Dear colleagues, now I'm going to make the brief report about NMR applications to wood and cellulose science. Unique properties of wood and cellulose generate a high demand for use in many different fields, especially for the development of commercially profitable composite materials with desired properties. Knowledge about features of supramolecular structure, porous system, and sorption capacity of wood and cellulose is necessary to predict the operational properties of final products. For the detailed study, researchers often apply combinations of various methods of physicochemical analysis. However, within this framework of this report, we will consider only a few time domain NMR techniques, as well as results of estimation of these parameters. First of all, I would like to show the main experiments that we will be mentioned further in the report. To solve the problem of ringing time of a receiver, solid echo and magic sandwich echo were developed. For systems with higher molecular mobility, Karp-Parson-Maybaum GIL sequence is used. This experiment makes it possible to eliminate the contribution of permanent magnet inhomogeneity due to the observation of repetitive echo signals. Here, we mostly focused on the analysis of magnetization decays, in which the contributions from the solid phase of wood or cellulose and water are unambiguously distinguished. Meanwhile, the fitting of magnetization decays is produced by models including intensity and transverse relaxation times. However, such models are not always applicable. In this case, reproducible results can be achieved by the amplitude averaging approach. The slide shows the free induction decay of cellulose with adsorbed water. To calculate the contribution of each cellulose phase and water, 3 points are considered. These points, S, M, L, correspond to amplitudes average over certain time ranges. In this way, the crystallinity and amorphicity of cellulose and wood can be calculated. It should be noted that the amorphous phase we mean surface cellulose chains. In case of cellulose, of course. Earlier, we showed that transverse dimensions of cellulose crystallites are related to its crystallinity. Spin diffusion experiments have been developed to estimate sizes of crystalline and amorphous domains. Studies of multi-component polymer systems require a thorough analysis of possible magnetization transfer ways, as well as the selection of NMR signal region for constructing and interpreting the diffusion curve. The most common approach to stimulate spin diffusion from amorphous to crystalline domains is the Goldman-Shanks pulse sequence. This method makes it possible to register the polarization transfer between adsorbed water and amorphous phase, as well as amorphous and crystalline phases in the cellulose water system. For another case, the magnetization transfer from crystallites to amorphous regions of cellulose, the two-quantum filter is applied. On the slide, you can see the results of this experiments adaptation for the study of spin diffusion in cotton cellulose. Then such curves proceed via analytical expression. For estimation of the transverse dimensions of cellulose crystallites, we offer to apply the equation 1. that characterizes the diffusion path of propagation of non-equilibrium spin polarization from the center of crystalline formations to their surface in the experiment to measure T1. It's assumed that the spin coefficient in cellulose crystallites is constant. There is an ambiguous correlation between the magnetization transfer time tau and the spin lattice relaxation time T1 of cellulose solid phase. Both parameters describe the process of spatial alignment of inhomogeneous spin polarization in systems of localized magnetic moments. Taking into account the assumption of proportionality between tau and T1, as well as the equation 1, sizes of cellulose crystalline aggregates can be determined as equation 2. For the practical implementation of this dependence, it's necessary to consider that the measured spin lattice relaxation time of cellulose cannot be less than T1 of its amorphous parts. And also the crystallite size is limited from below by the size of indivisible fibrillar formation, denoting which by Y0. At this slide, you can see the ad hoc equation for cotton cellulose and the corresponding parameters, value parameters. According to the known relation between the crystallinity of cotton cellulose and crystallite sizes, see equation 3, we can obtain the equation 4. So it becomes easy to practically estimate its crystallinity from the measured T1. Amplitudes of magnetization decays can also be used to determine the proton density of samples. Based on the fact that cellulose having a predominantly crystalline structure contributes to the rapidly decaying region of NMR signal, it's possible to determine its content in wood. It is known that influence of water on the cellulose structure is reflected in the physicochemical and mechanical properties of finished product during its operation under different temperature and humidity conditions. So it's extremely important to measure water content. Via the amplitude averaging approach, one can estimate the absolute and relative water contents. By simulation, the water absorption in a slit-like core of cellulose, we find out that adsorbate forms 3 fractions with fundamentally different adsorption potentials. In this slide, you can see that modeled water isotherm shows the 3 components corresponding to 3 different water fractions. This conclusion is confirmed by the presence of 3 components in the decays or in CPMG experiment with the ultra-short echo time equal 60 microseconds. At its lower values, the signals contain an undesirable contribution from surface cellulose molecules. And with the increase of 2 tau, the resolution of relaxation decay from strongly bound water decreases. These water fractions are not characterized by rapid exchange, so there is a clear separation of their contributions. The envelope of echo signals amplitudes is well described by the sum of 3 exponential functions. Based on the difference in molecular mobility, we assume that molecules of the first water fraction are strongly bound to the surface of cellulose porous walls, and the second and third ones are stored predominantly on strongly bound water in meso and macropores respectively. In this case, it's respected the well-known thesis that movements of water molecules in adsorption layers become freer as they move away from the absorbent surface compared to the mobility of strongly bound water. Due to the heterogeneity of cellulose pore sizes, the number of water molecules in each of fractions differ from each other. The figure on the left shows the change in proportions of these fractions converted to moisture contents with increasing water activity. The absorption process in cellulose includes several mechanisms. So the curve of the first water fractions appears to be close to the real adsorption isotherm, which directly reflects the interaction between adsorbent surface and adsorbate. In the same figure, the water absorption isotherm of cotton cellulose is shown for comparison with NMR data. In fact, it coincides with the sum of contributions from these three water fractions. A significant result in study of the cellulose water system via CPMG experiment was the revealed linear relation between the strongly bound water content and proportion of the medium component in MSC signal from amorphous regions of cellulose. This result confirms the earlier hypothesis about the identity of amorphous phase and surface of cellulose crystallites. In the end of report, I would like to show that it's also possible to determine thermodynamic and energetic characteristics. On the left side of the slide, you can see the results of estimation, the thermodynamic characteristics for below water absorption on cellulose. Moreover, NMR sensor in conjunction with considered techniques can be applied to optimize production processes when monitoring the structural and physicochemical parameters of wood and cellulose. Now, that's all I wanted to say. Thank you for your attention. I don't hear the
Включите микрофон.
Oh, sorry. Yes, thank you very much for your talk. And now the session is open for discussion.
Thank you.
Vladimir Ivanovich, please.
Thank you. Micropores and macropores are characterized by the similar spin relaxation times. How can you distinguish them?
No, in our case, we separate these pores by the corresponding mobility of water mobility. It means we separate two different transverse relaxation times because of in macropores water molecules have more freer motions.
How can you explain that in different in the size pores we have the same, approximately the same relaxation times?
But there is let's say a big difference between these times. In the second case, for mesopores, it's characterized the T2 of some hundreds microseconds, but for T23 is characterized the time of milliseconds.
I think it is difficult to have some certain meaning, or maybe it is not a simple task to distinguish these pores. I think so. Thank you.
Okay, thank you for your question.
Thank you.
I have a question, but
Ah.
okay.
Okay.
It's not a question. It's
Okay.
just a suggestion.
Okay.
According to our experience in Kazan Federal University, if you warm up your wood, yes, in vacuum, you can observe the EPR signal. And this EPR signal is a rather strong one. And certainly in combination with your NMR techniques, certainly you can make very important conclusions. It's my suggestion. It's not a question at all. Thank you.
Thank
Yeah,
you.
Murat Salihovich, very interesting. I just need to tell that in the beginning of May, Maria will present her doctoral thesis in KGTU. So maybe we will step by and talk about the joint.
No problem.
Preparation.
We have a rather good publication concerning such investigation in German scientific journal, Science of Wood, or something like this. I don't remember exactly. It was published 5 years ago. Okay.
Great.
Nice.
Thank you.